Have you ever stopped to think about how a massive machine, weighing over 500,000 kilograms, something that seems far too heavy to ever leave the ground, glides smoothly through the sky for hours over vast oceans? It almost feels unreal. Yet the science behind it is even more fascinating than it appears. Today, we're diving into the incredible story of flight. How does such an enormous aircraft stay suspended in the air? What invisible forces keep it up there? And why doesn't it simply fall or overheat and fail? By the end of this journey, the next time you watch a plane take off, you'll see it in a completely different light. Because what's happening is far more extraordinary than most people realize. To truly grasp the scale of this, consider one of the largest passenger aircraft ever built, the Airbus A380. At takeoff, it can weigh around 575 tons. That's comparable to the weight of a fully loaded train. And yet, this gigantic machine doesn't just lift off. It cruises at altitudes of around 35,000 feet, traveling at speeds close to 560 miles per hour for 10, 12, even up to 15 hours at a time. At first glance, logic would suggest that something this heavy should remain firmly on the ground. But physics tells a very different story. The journey to modern aviation wasn't instant. It's the result of more than a century of discovery and experimentation. Early attempts at flight began with hot air balloons, which could float but offered little control. True flight required something more. In the 19th century, Sir George Cayley introduced a groundbreaking idea. Lift and thrust are separate forces, and wings must be shaped in a specific way to generate lift. Later, Otto Lilienthal conducted hundreds of glider experiments, risking his life to understand curved surfaces. Then came a historic breakthrough. In 1903, the Wright brothers achieved controlled flight with a heavier-than-air machine. Their aircraft stayed airborne for just 12 seconds, but that brief moment changed human history forever. From there, aviation technology evolved rapidly. During World War I, aircraft design advanced significantly. Wood structures were replaced with stronger metal bodies, engines became more powerful, and aerodynamics improved. By 1952, the de Havilland Comet became the world's first commercial jet airliner. Then in 1970, the Boeing 747 revolutionized global travel, connecting continents like never before. Years later, Airbus introduced the A380, pushing the limits of size and engineering. Despite all these advancements, one fundamental principle has remained constant. Flight depends on balance. So how does this enormous metal structure stay in the air? The answer lies in four key forces. First, gravity, also known as weight, pulls the aircraft downward. Second, lift, generated by the wings, pushes it upward. Third, thrust, produced by the engines, moves the plane forward. And finally, drag, the resistance of air, works against that forward motion. Flight is essentially a constant balancing act. When lift equals weight, the plane maintains its altitude. When thrust balances drag, it maintains a steady speed. Any change in this balance affects how the aircraft moves, causing it to climb, descend, accelerate, or slow down. There's no magic involved, just precise control of these forces. But the real question is, how is lift actually created? You may have heard a simple explanation, that air traveling over the top moves faster because it has a longer path, creating lift. While that idea is popular, it's not entirely accurate. The truth is more complex and more interesting. Aircraft wings are carefully designed with a special shape. The upper surface is curved, while the lower surface is flatter. Additionally, during flight, the wing is tilted slightly upward. This is known as the angle of attack. As air flows around the wing, it moves faster over the curved top surface, reducing pressure there. Meanwhile, the pressure beneath the wing remains higher. This difference in pressure pushes the wing upward. But that's not the whole story. The wing also deflects air downward. And according to Newton's third law of motion, every action has an equal and opposite reaction. So when the wing pushes air down, the air pushes the wing up with an equal force. In reality, both effects, pressure difference and downward deflection of air, work together. Their combined result is what allows a plane weighing hundreds of tons to stay in the sky. Another key factor is the angle of attack. During takeoff, the pilot pulls back on the controls and the nose rises slightly. This increases the angle of the wings, strengthening airflow and boosting lift. However, this increase has limits. Lift doesn't keep increasing indefinitely. Beyond a certain point, something critical happens.